Here is a matching type question. Study the items in both columns carefully. Try to work out the matching before we solve it together. Let us first understand the key concept here. SN2 reactions proceed via a backside attack transition state. The rate depends critically on steric accessibility of the electrophilic carbon. Less hindered, less substituted, carbons react faster in SN2. First structure, cyclopentylethyl bromide, the Br is on a primary carbon at the end of a 2-carbon chain attached to cyclopentane, cyclopentyl CH2CH2Br. The carbon-bearing Br is primary and relatively unhindered. The cyclopentyl group is 2 carbons away. Second structure, 1-bromo-1-ethylcyclopentane, the Br is directly on a tertiary carbon, C1 of cyclopentane, which also bears an ethyl group. This is a tertiary alkyl bromide, extremely hindered toward backside attack. Reasoning: primary substrates react far faster than tertiary substrates in SN2. The cyclopentylethyl bromide, primary, will undergo SN2 much more rapidly than 1-bromo-1-ethylcyclopentane, tertiary, essentially inert to SN2. Why the other fails? Tertiary halides have 3 substituents blocking the backside of the C-Br bond, making SN2 essentially impossible. B. SN1 reaction comparison. Let us first understand the key concept here. SN1 reactions depend on the stability of the carbocation intermediate formed after ionization. The leaving group also affects the rate. Better leaving groups, lower C-X bond strength, more stable X, increase SN1 rate. The carbon skeleton is identical in both, tertiary butyl, so the leaving group is decisive. CH3, 3C, Br versus CH3, 3C, both form a tertiary carbocation. The C-I bond is weaker than C-Br, bond dissociation energy, C-IC-Br, and I is a better leaving group than Br, I is a weaker base, more stable anion. Therefore, CH3, 3C, I ionize faster. Reasoning: the iodide is a superior leaving group relative to bromide. With identical carbocation stability, CH3, 3C, I undergoes SN1 more rapidly. Why the other fails? CH3, 3C, Br forms the same carbocation, but the C-Br bond is stronger and Br is a poorer leaving group than I, so it ionizes more slowly. C. SN1 reaction comparison. Let us first understand the key concept here. SN1 rate depends on carbocation stability. In bicyclic systems, bridgehead carbocations are extremely destabilized because Brett's rule prevents the needed planar geometry at a bridgehead for sp2 hybridization. The ring constraints prevent flattening. A secondary, non-bridgehead, carbocation in the norbornane system is far more accessible. First structure, to bromonorbornane, Br is at C2, a secondary, non-bridgehead carbon. Ionization gives a secondary norbornyl carbocation, which, while strained, can still form and is even assisted by neighboring group participation, non-classical carbocation stabilization. This is feasible. Second structure, 1-bromonorbornane, Br is at C1, the bridgehead. Ionization would require a bridgehead carbocation, which violates Brett's rule for small bicyclic systems. This carbocation is essentially inaccessible due to ring geometry preventing sp2 hybridization at the bridgehead. Reasoning: to bromonorbornane can ionize to give a non-classical norbornyl cation. 1-bromonorbornane cannot ionize to give a Brett rule violating bridgehead cation. Hence, 2-bromonorbornane undergoes SN1 far more rapidly. Why the other fails? Bridgehead bromide in norbornane is essentially inert to SN1 because the resulting bridgehead carbocation is geometrically impossible in the small bicyclic framework. Therefore, the correct answer is A. Cyclopentylethyl bromide, cyclopentane CH2CH2 Br, B. CH3, 3Ci, tert-butyl iodide, C2-bromonorbornane, Br on a ring carbon adjacent to the bridgehead, C2. Therefore, the correct matching is A matches cyclopentylethyl bromide, cyclopentane CH2CH2 Br, B matches CH3, 3Ci, tert-butyl iodide, C matches to bromonorbornane, Br on a ring carbon adjacent to the bridgehead, C2.